So this is the pendulum experiment, and of course you're going to measure several lengths and let it swing. I'm just going to show one example. Earlier I made myself a mark here of exactly 100 centimeters, so now I'm going to measure down. So I put the end of this one, the measuring tape on here, and I'm measuring 96 centimeters to the middle of my weight, because you're not supposed to measure to the bottom or to the top. You have to measure to the middle of it, where the center of mass is. In this case, you actually notice that I did make a mistake. The measuring tape doesn't start at the end of it, but there is a zero mark, so that's where I have to start. And I just wanted to show that typical systematic error that you could do in this experiment. So I'm actually measuring 98 centimeters on top of the 100 centimeters I had earlier, and the lab sheet perhaps says 200 centimeters, but I would use 198 centimeters instead. Remember that those are always benchmarks that I give, the 25, 50, 75, and so on. So use something that's relatively close to it. I'm using 198. Now I'm letting it swing forth and back, and I'm going to start, and keep the angle small. I'm going to start right now. And then 1, 2, 3, 4, 5, 6. It says on the lab sheet 20 times. 7, 8, 9, 10. Earlier when I strung it up, 11, 12, 13. I didn't lose count, did I? 15, 16, 17, 18, 19, 20. Of course, you're going to have a different kind of stopwatch, or perhaps you could just go with the clock. With stopwatch, you increase the accuracy a little bit. With a normal clock, you can get probably to the closest second. I measured 53.8 seconds, so I rounded to 54 seconds for 20 swings, which means when I put it on the paper, it's going to be 2.7 seconds per swing. If I actually had a miscount, if I actually counted 21 or 19 instead of the 20, I will notice that later when it comes to the calculations. As I said, as you look at the lab sheet, you should come up with 982, close to it, for gravity, 982 centimeters per second squared. But if I come up with something that's widely off, I could attribute it that I made a miscount. Earlier, when I strung this up, I noticed that the string was twirled, and it untwirled itself, and that actually could make a difference. So wait till it's kind of stable. Basically, that's actually it that you are going to measure here. For the pendulum, you're measuring the time, you're measuring the length as accurately as you can, and yeah, you could have the systematic errors that I showed you earlier of measuring to the bottom while you're measuring where you're supposed to measure to the middle. You have to measure exactly from the pivot. You could have the systematic errors of hitting the stopwatch too early or too late. You could have random errors of, well, simply measuring, and then you have to say, well, how accurate did I actually measure, plus minus 1 centimeter. And then here on the stopwatch as well, the random error of, did I actually hit it right now, or did I just hit it a moment too late or too early, and I'm not exactly sure about it. Anyway, that's actually all I have to say about the pendulum, because it's a really easy experiment to put up and to measure. And I do the calculations in a different recording. Thanks.
In this recording, I'm going to use some data from previous physics labs to look at significant figures, units, errors, and those are qualitative and random versus systematic errors. Also quantitative, that is computational errors. Furthermore, outliers, and then I'm also going to look at average and standard deviation and how to compute them. Okay, let's start out with these data, and two things are happening here. Look at how many significant figures there are, there are 6 significant figures all the way through, and also that all of these results are systematically larger than what the acceleration due to gravity should be, which is 982 in Alaska or 980 in the continental US. I left out most of these data taken by the students to mostly focus on these here, on the results, what students had calculated. This is what they measured. Measured time for significant figures. They divided by 20 because they had 20 swings. Stays with 4 significant figures because that's how accurate they measured. And they measured the pendulum length to 3 significant figures. And because of this one here, the result has to be 3 significant figures. So this one here should be 1010, and then it goes on here. 3 significant figures is the lowest, so this one here should be 1070, and so on. I'm going to fix this here for a moment, just stop my recording. Okay, so I fix these here, 3 significant figures, because this one here is with 3 significant figures. The other thing to point out here is that these are systematically too large, so the students must have done something wrong. I'm assuming that they measured maybe 1 too many swings or 1 too few swings and therefore calculated the wrong number. A few other things to point out, or at least one other thing to point out, is the units. Students don't have to attach seconds here and centimeters here because those are already listed on top of the table. So if they are listed on top of the table, don't attach them again, but it's clear that all of this here is in centimeters. Alright, let's move on to the next data set. So what these students did, I'm going to move this just a little bit higher still, there we go, is they measured the time to 4 significant figures divided by 20 swings. They measured the pendulum length to 3 significant figures, and therefore the result has to come out to 3 significant figures. And as you can see, they did that correct here. I guess it gave 1 too many, so 1040. This one here is also the outlier. If you look at all these data, then you can see that 979, 86, 79, 87, 75, kind of around pretty close to each other, and this one here is significantly off, and therefore it should be taken out and considered an outlier. And it's totally appropriate to cross that out and disregard it. Something must have gone wrong here, and therefore take it out because all the other results show that they are really close to each other, and the students must have done something or everything correct. And of course there is a certain measurement error here that gives this slight random spread. Definitely not a systematic error, but some random error which can be attributed to that you can only measure the pendulum length to the closest millimeter or 1/10 of a centimeter, and the stopwatch gives the time to the closest 1/100th of a second. And of course there's also the reaction time of about 0.2 seconds in there, which obscures a little bit the decimals here on the time. Alright, let's look at computing the average, and that should be relatively simple. Just add these results. There are 2, 4, 6, 10 valid results. Add them all, divide by 10, you come up with the average. But I also want to determine what the standard deviation is, which then would become the error. So I have to do it a little more fancy. On a graphing calculator, open one of these squiggly parentheses and then type in the data. Of course, that obviously takes a while. Going to pause here for a moment and put these in while I'm pausing. And the last data point. Close these squiggly parentheses, and store the data in list L1. When I hit enter, it's just going to give me those data again. And I'm going to go to stats, calculate one variable statistics. I only have one variable here. And I'm going to hit enter, and I need to tell it use list L1 that I just stored it in. And here are the results. The average is around at 983 centimeters per second squared, and the standard deviation is 4. So I'm going to enter these here. 983 I just read off, plus minus 4 centimeters per second squared. Here I need to truncate this here to 4 because I'm adding all these data, and as I'm adding these here, the rule for significant figures is that I have to truncate after the last accurate digit, and that would be the ones back here. So after the 3, which means the standard deviation also has to be truncated here. There will be no decimals after that. So 983 plus minus 4. And of course, when you look at this here, by obeying the rules for significant figures, this also looks kind of nice, that you can look at it directly and say 983 is just a little bit higher in Alaska than what it should be in Alaska, and then plus minus 4, there is no addition or subtraction of decimals, superfluous decimals that shouldn't be there. And as I said, it really looks kind of nice the way it's written this way. What if you don't have a graphing calculator? So I googled online scientific calculator, and you can see I clicked on quite a few here. Turns out as they look kind of like a scientific calculator may look like, but it seems like none of them seems to have statistics functions. So instead I googled online statistics calculators, and this one here works. I clicked on this one here, I guess because it gave me a bigger editor screen, and I don't need any of this, but this is what I need: mean, not mean deviation, standard deviation, and actually the mean. And let's see, I have to find the data there, and let's see if I'm able to squeeze it all on one screen here. Yep, maybe so. So I'm going to type in 979, 986, and so on, all separated by a comma. But notice I can do a shortcut. I can just type in 79, 86, 79. Why am I allowed to do that? Well, because all my numbers start with 900. So I can just say at the end, okay, I'm going to come up with an average here between these numbers, and then just add the 900. It's going to be quicker to enter, and also less error prone as I put these data in. So that's kind of an alternative to putting always at 900 there. Okay, do I have all of them for a 10? Okay, then I'm going to hit compute, just a little bit off the screen. There it is. And there is that same mean or average, 82.5 rounded to 83, so 983 plus minus 4. So same result as with the graphing calculator. Okay, let's look at some more data. So what I got on for these here, these students have more of a spread in their data, and we can already see that this is probably an outlier, and probably here's another outlier, and these here look pretty good, and then we'll see what we come up. For this one, I took one of the student data out and I put my own in that comes from my video where I measured 53.8 seconds, and the period is 2.69 seconds, so this divided by 20, and the length is 198 centimeters, and then I calculate, and I'm going to come up with 4 pi squared divided by 2.69 squared times 198, and I come up with 1080, and that is quite a large outlier. And I went back to my video and noticed that indeed I had not counted 20 swings, but instead I had counted 19 swings. So I made a mistake right there, and that is fortunately easy to fix. So it's going to be 53.8 divided by 19 instead of 20. So it's 2.83 right here. I don't have to retake that measurement as long as I can figure out that's what all my mistake was. If I know that I have really timed it for 19 swings rather than 20, then I can fix that, and it's not going to upset my results as long as I'm able to fix it. So 2.3 squared here, and it comes out to a much nicer 976. All of a sudden I don't have an outlier anymore. So I'm thinking that perhaps this is what happened here on some of these results. Maybe they measured half a swing too few, so 19.5 swings, and here maybe they measured like 20.5 swings. Notice that, oh, here I plotted these data, and we can kind of see here's kind of like nice data here, some kind of spread in here, but not too bad. But here is definitely an outlier, and here are 3 outliers. So the data are still useful, but I have to kick out a few of them and consider these to be outliers. And then do the same calculation for the average and the standard deviation as I did before. So again, I put these on the outside here, and here we go. And again, I have all numbers in the 900s, so I can just do the same thing as before. 79, 84, 79, and I'm going to double check my data. Yep, looks like I entered them correctly. I'm going to hit the compute button, and there's my average, so it's going to be 981 plus minus 5. So the data that did survive after kicking out the outliers yield 900, what was it again, 981? Yeah, plus minus 5 standard deviations, just slightly larger than what the other students had. In the conclusion, this is what I'm writing. I guess I didn't have 984, I had 983 earlier, 983 or 982, depending on which data set I'm using. It's really close to the accepted value of 982 for Alaska, within actually it's 0.1%, really close. And then what I should write in here is avoid systematic error, measuring the pendulum length by putting measuring tape end to end, making a mark bottom or top of the pendulum weight, so you have to measure to the middle of the pendulum tape, middle of the pendulum weight to the suspension point. Measuring the time, start too late, keep the wrong count, these kind of things. The random errors could be length of the pendulum. Oh, I'm sorry, this is off the screen. Random errors could be length of the pendulum within 0.5 centimeters, or actually 0.1 centimeters, hitting the stopwatch within one's reaction time, usually about 0.2 seconds for the average person. I also looked this one up here and got several quotes that say that's about a person's average reaction time. And one thing about this one here for this specific experiment is that if you're likely to start 0.2 seconds late, then you're also likely to stop it 0.2 seconds late. So the reaction time actually subtracts itself out, and it really is a random error in the hundredth of a second, which makes the result, the measurement and the result, more accurate. This is a recording to determine the average and the standard deviation of some data, and I'm going to do it several ways. One is with an online statistic calculator, then with a TI-84, and then, so to say, by hand. We're still using the calculator though, but I'm using the theory behind the standard deviation. Anyway, let's get started. These are some old student data that I still had, and I took off the obvious outlier here, and then we can see that these are the computed results for the acceleration due to gravity. And I'm going to start with a scientific calculator. Respectively, I'm going to try. When I googled online scientific calculator, I tried quite a few here, and none of them offers me a statistics function. So if you have a scientific calculator, try to figure that out. Respectively, go to an online statistics calculator, and I chose the second one, I think because the screen is bigger. So here we go. I don't need the variance, but I do need the mean, and I do need the standard deviation, just a tiny bit off the screen. There we go. Okay, now I'm going to put in the data, and I would write 979, 986, 979, but notice they all start with a 900, and I'm just going to be lazy, and I know that my average is going to be 900 something, and I'm going to skip the 900 itself and just type in 79, 86, 79, and so on. When you do a lot of data crunching, tricks like that come in handy. So I'm going to type these in here: 79, 86, 79, 87, 75, 86, 86, and 79, and I got 368 data, 368, yeah. And then I'm going to just hit compute. And there it is. The mean, the average is 82. Obviously that means 982 centimeters per second squared, and the standard deviation is simply the 4 here, which means 982 plus minus 4 centimeters per second squared. And that's with a statistics calculator that I found online. So that was pretty straightforward. Now let's do the graphing calculator, in case you are using a graphing calculator. So here's the TI-84, and I'm gonna put in the data. First I need to open these curly brackets, and I'm gonna type in the data: 79, just like before, 86, 79, 87, 75, 86, 86, close that. Now the other online calculator I found was of course straightforward, because it's already programmed to do exactly that, and really quick. On any other calculator, including graphing calculator, it takes a few more steps to achieve that. So I'm gonna hit here, save it. Whoops, before I do that, store. Oh, what do I do now? Do that again. Store to L1. There we go, there it is. Hit the stat button, go over to calculate. This is what I need: one variable statistics. I need to tell it to use the L1 data list, by the way. L1 is down here after hitting the second button, and the store that I used a moment ago is right here. So here's the L1. Hit enter, and there it is. Again, 982 plus minus 4. Right there's the sigma, the standard deviation. Okay, if I do it by hand, which means I'm still going to use the calculator, of course I add these numbers here. And as far as determining the average, that is really the easiest way to do it anyway. Just add all the data. And then divide the result by the number of data, and there were 8 of them. And there it is again, 82, which is 982. Notice as I'm crunching all these data, it really comes in handy that I skip the 900 and just add that at the end. Okay, doing it by hand for the standard deviation takes quite a few more steps. So I'm just going to get my data points back that I can look at them. I don't actually need the 657 here, but I need these 79, 86, and so on. And I need that the average was indeed 82. So let's see, let's get that back. There we go, 82. And what I'm going to do now is I subtract 82 minus 79, 82 from 86, 82 from 79, and it doesn't really matter if I do that. In which way I do that, if I get a positive or negative number, because I'm going to square them anyway, and the square of course always is a positive number. So 82 minus 79 is 3, and I need to square that. 86 minus 82 is 4, and I need to square that. 79, 82, that's a difference of 3. 87, 82, that's a difference of 5. 75, 82, that's a difference of 7. 86, 82, difference of 4. That's how I should have explained it earlier. Just take the difference between the two. 4 again, and 3 squared. Hit enter. Divide by the number of data, which is 8. And finally take the square root of that, and that's the standard procedure to figure out the standard deviation. And I come again up with 4. So 982 plus minus 4. These are the 3 ways that I wanted to show it: graphing calculator, by hand, so to say, as well as a statistics calculator. And the only thing I couldn't find was an online scientific calculator that would actually simulate that. But here it is, 3 different ways of figuring out the standard deviation and the average. This is an example for an Excel analysis, and the data are taken from the Pendulum lab from a couple of students who came up with very good results, because the Pendulum experiment is a very accurate experiment. Okay, and this is the time that they measured. Here's the length of the pendulum, time in seconds, length in centimeters, and here are the first 2 data. And then I'm not going to type everything again, I'm just going to paste it in here. There we go. I clean this one up just a little bit. There we go. Just align it. There. Might just make it look a little better. All right. With these data, the acceleration due to gravity is determined, so in centimeters per second squared. And here's the algebra. So the pendulum equation is t equals 2 pi square root of L over G, and that needs to be solved for G. So I'm going to square everything and multiply with G, so a couple of algebra steps here in one. And then here's that where I said multiply with G. Okay, this one I'm going to use in a little while, so I'm going to box it in. And now I'm going to divide by t squared. So G equals 4 pi squared L over t squared. And this is what I'm going to use now, and as I said, I'm going to return to the boxed in intermediate step later. 4 pi squared L over t squared. So equals 4 times pi, this is how to write pi in Excel, squared, times L. L is this one here, so I'm going to grab this one here as cell B4, and then divide by the time, which is this one over here. So that is cell A4 squared. Enter, and I'm going to highlight this one here and pull it all the way down on the lower right hand corner. Whoops, yep, there it is. And I come up with a totally wrong result. And the reason that happened is that if you divide just by the t squared, well, that's the time for 20 swings, as the lab explained. That is not the period. So what I would have to do is I have to insert a column which is the time for one complete swing back and forth. And since there are 20 swings, then this one comes out to be the total time for 20 swings divided by 20 swings. There we go. And also pull it down. Looks nice. And now here what I would have to change, I have to grab this cell over here, B4. That looks better. And I'll pull it down, and that looks pretty good. And I'm going to make this look nicer. There we go. This one here perhaps could be considered an outlier. I'm going to leave them in for now. You may want to consider looking at outliers for the data that you get. Okay, I'm going to calculate the average here. So equals average, and that goes from data D4 to D12. There we go. Hit enter, and I come up with an average of 978 centimeters per second squared. So that's just a little bit off, a little bit less than 0.5%. So here I can write average G there we go. Okay, I will do this in a second way by graphing the data. And as I said, I'm going to grab this one here. In fact, maybe I can literally grab it. Oh yeah, there we go. And what I'm going to do is, as I graph these data, I will graph them as a straight line, but I have to do a little bit of a trick here. I have to call this one here X, this one here Y, and when I graph this one as Y and this one as X, I get a straight line with a slope M, and that M here would be readily the acceleration due to gravity. and that's why I wrote it the way I did. So when you do your analysis, look at something similar so that you can graph it as y equals mx, and you can directly read off the slope, which in this case here is the acceleration due to gravity. When I graph these, let's see, there's one, and then I would put here on the y-axis 4 pi squared x, I'm sorry, 4 pi squared L, and on the x-axis I would put t squared, and when I graph these data I come up with something like this here, and then Excel will do a best fit straight line through it, and again the slope of this one here is gonna be g, relatively close to 982 centimeters per second squared. As I said, the student data were pretty good. Okay, so that's what I'm going to do in Excel now. Gonna calculate a couple of columns t squared and 4 pi squared times L and graph them. So let's see, t squared, and over here that was 4 pi squared times L. That's just the header for these two columns. So here I'm going to grab cell B4 and square that. Here I'm going to grab 4 pi squared times cell C4. Okay, I'm going to highlight both, pull them down. There we go. Don't need that many digits here. That'll be fine. Maybe one here, one more here. There we go. Okay, and then I graph these data. And it would make sense to put the graphing under data, but in Excel it's under insert. There we go, insert, and then we can see the various way of graphing here. It is always going to be a scatter graph that is not connected, that the dots are not connected. So here we go. Okay, now I have to pull this down a little bit, so actually pull it up a little bit. Okay, gonna go. I don't need that. I don't need these lines here. Make it a little bit tighter so we can see more. Okay, so here are the data plotted. And again, this axis here is t squared. This axis here is 4 pi squared times L. In themselves, they don't have much of a meaning, but they just give me the means of coming up with a slope here that will be g as shown in the algebra. I'm going to right click on these data, and down here it says add trend line. I'm going to do that again just to make sure that it's on the video. There it is, add trend, right click, add trend line. Okay, here are the options. Linear is what I want. And then display the equation on the chart, display the r squared value on the chart. I'll explain it in a moment. And there we go. In fact, there is my r that I wanted. 978.86 compares to the average, I think it's still here, of 978. So you come up with two results, one from the Excel analysis and one from the average. The r squared value tells us how good the data are. The closer this number is to 1.000, the better the data are. In fact, in physics, it's pretty much unacceptable to have an r squared value below 0.990. So it has to be this good or very close to being this good.
Okay, so this is a very long pendulum, and while I'm talking here, I'm writing the numbers down and I'm reading off here. Might as well. And we measured this one earlier to all the way up, if you want to film all the way up there. And so we suspended it from way up there, and we measured a total length of 415 centimeters. And while I'm doing this, I'm still jotting these numbers down. And so 415 centimeters to the middle of the lead ball. And then we recognize that the string adds some weight to it, which pulls the center of mass up. Therefore, we figured that we have to actually calculate that, and the actual center of mass is 1.8 centimeters up. So the total length of the pendulum is 413.2 centimeters. And then we put that photo gate here, and that's what I keep writing down here, because I didn't learn how that one actually could possibly record the data, and I think I have like plenty of data here. And so this one here records really, hopefully really accurately, how long it takes the pendulum to swing through here, and we should come up with a really good result for the acceleration due to gravity. Okay, I think that was actually what I wanted to talk about.